Hi, this week we're going to start a new topic. We're going to be actually discussing Taylor and Maclaurin series of any function. But of course we're going to start with something simpler, which is Maclaurin series of a polynomial function. Of course we will be then complicating this situation until we reach a conclusion that is going to be given by Taylor series. And this series, Taylor series with Lagrange remainder, is something that we are using very, very often in economics. At this moment, it is going to be very hard for me to give you even a simple economic example of application of that. However, you should remember that the possibilities and actually the application of those series are incredible. We use them in order to solve systems of difference and differential equations. They are non-linear, and we want to assess the properties, dynamic properties of equilibrium. Consequently, we use them very often in general equilibrium models. So models that are supposed to explain behavior of one or even many different economies at the same time. I just want to, so even though what I'm going to be telling you today is very, very abstract, later on in economics we use it everywhere. Next semester, in dynamic economic analysis, we will be using polynomial series, Taylor and Maclaurin series, to evaluate the value of E. However, the most, I would say, prominent application of Taylor series that you're going to see is going to be during the fourth semester, when, using the Taylor series, we're going to obtain a very, very interesting result. This result is that if I'm going to take E to the power pi times I, where of course we remember that I is square root of -1, it turns out that this is equal to -1. Okay, look, this, what you see over here is one of the applications of Euler's relations, and this is known as the most beautiful equation in economics, because look, we're getting three constants, E, pi, and I, and we are taking E to the power pi I, so we are taking a number to the power, to some power, and as a result we obtain a negative number, something that we are not seeing in regular considerations of these functions. But of course, look, before we get to this, we need to start somewhere. And we're going to start with Maclaurin series of a polynomial function. Okay, so look, here we've got the polynomial function. So f of x is equal to a constant, x0, right? Plus a1 times x, plus a2 times x squared, a3 times x cubed, a4 times x to the power of 4, until an times x to the power of n. Okay, this is already very nicely organized function, right? Because we see that we are getting from x's to smaller powers to bigger powers, right? However, remember one thing. There's even more, this is even better organized than meets the eye, because of course here we've got x to the power of 1, which again means that the two index and the power are the same. And over here we could have a0 times x to the power of 0, which of course is 1. Okay, and what we want to do today is to take this function and rewrite it in a different way that would give us essentially the same function. And of course, we're going to obtain this by means of differentiation. So first thing we're going to do over here is that we're going to find first derivative of this expression. Okay? So here we've got just a constant, so it's gone. Now, so this is 0. Here we've got a1 times x to the power of 1, so we've got a1. Okay, then what happens over here? Plus, we've got 2a2x. Then we will have plus 3a3x squared plus 4a4x to the power of 3. And the last expression over here will be n, or any n, times an times x to the power of n minus 1. Okay, this is actually a very, very easy to function that is really, really easy to differentiate. So let's do it a couple more times. Okay, so now second derivative. Now this is gone. All we have is 2a2. Now over here we've got 3 times 2a3x. And what do we have over here? We've got 4 times 3a4x squared plus, and the last element would be n times n minus 1 times an xn minus 2. Okay, so I hope you see that with two differentiations, we've actually lost two coefficients. First a0, then a1. Of course, now that we're going to calculate third derivative, we should lose one more. So, this part is gone. And what do we have here? 3 times 2, a3. That's it, right? Or, I could also write it as still would be true, right? Then, this expression changes to 4 times 3 times 2. Of course, I could also put times 1, an x plus, and of course here we will have n times n minus 1 times n minus 2 times an xn minus 3. Okay, let's carry on. Let's continue with differentiation. Now we're going to take the fourth derivative. So again, we are losing one more component here. Of course, this constant that you see over here. And now this is going to be our new constant, right? And what will be the derivative of the expression that would stand over here? Right? It is kind of easy to get, right? We would have this is, of course, this is 4. I'm sorry, I'm writing horrible force. And this would be 5 times 3 times 2 times 4 times 3 times 2 times 1 times a5 x. Right? And then over here we would have times n minus 1 times n minus 2 times n minus 3 an x to the n minus 4. Okay, I hope you can notice what is happening. There are two things that are important. First, we are losing components that are associated with the constant, and of course, with every differentiation, we get one more new constant, right? It's going to be gone in the next differentiation. And second, we've got these numbers that appear over here, and they are in a very nicely organized. They are here in a very nicely organized fashion, right? 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1, right? We clearly see that this pattern over here is also represented for the last component, because we have n minus 1, n minus 2, n minus 3. Okay, so how many derivatives can we take here? Meaningful derivatives, of course we can take them forever. However, if I'm going to get to derivative n, because this is 4, I'm sorry for my horrible 4, so I'm going to take nth derivative. What I'm going to have, look, every component with n lower, with number lower than n is gone, right? So what will I have? What will I have as my last component? Well, the only last component will be associated with the last expression, right? How many differentiations we've done? N, right? So we're going to have here n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times, and look, of course here we are doing the differentiation n times, so we need to go to here. 5 times 4 times 3 times 2 times 1 times a. Okay, so look, this has shown us that after consecutive differentiation, we're going to run out of x's, and out of the last component, so our last constant that we're going to get is the expression that we see over here. Okay, now there is one more step we need to take. Well, what we need to do now is to evaluate the value of the function and each consecutive derivative at 0. Because, okay, we will get why we need it. Okay, so first, let's start with f of 0. How much is f of 0? Look, if we substitute 0 for x's, this is all gone. All we've got is a0. Okay, now, if I evaluate first derivative at 0, what am I getting? Look, I'm getting here a1. Every other expression is with x, so it will be 0. So I got that this is a1. Then, in case of the second derivative evaluated at 0, now if I substitute zeros for all the x's, I'm going to get a constant. So it's 0. Then, if I'm going to move to third derivative, evaluated at 0, right? Again, over here, all the expressions with x's are gone. All we have is a constant. Okay, and over here, 1 times a0, this would be true, of course. Here I can also write 1 times a1, and over here, I'm going to replace this with 2 times 1 times a2. I hope you know where I'm going with this, but before I explain everything, let me just finish with the derivatives. Okay, so next derivative would be fourth derivative. And where do we have fourth derivative? We've got fourth derivative over here, right? So we've got, if I evaluate it at 0, again, all those things are gone. All I got is 4, 3, 2, 1, a4. And look, can we guess what will be derivative number 5 evaluated at 0? Well, it would be 5 times 3 times 4 times 2 times 1 times a5. Okay, and the last derivative we've got here to evaluate, well, is derivative f n. So nth derivative evaluated at 0. And of course, this is the one that we've got over here. So this is going from n minus 1, and multiplying until 3 to 1, a n. Okay, so I hope you can notice, I hope you have already noticed that all those coefficients that we've got over here got some numbers assigned to it. Those numbers are strongly connected with differentiation. And the best way is to see it over here. Look, if I have variable x to the power of n, when I differentiate it, this variable, I'm going to get n times x to the power n minus 1. Then, if I differentiate this, n times n minus 1, x n minus 2. And look, if I'm going to be going like this until we ran out of x's to differentiate, we're going to have expression exactly like this. However, I hope you can see right away that it is very, very long way of expressing this very simple operation. This is why, in order to make this more concise, we can easily use the concept of factorial. Okay, so what is this factorial? I hope you've seen it in high school, but let me remind you a little bit. So factorial, of course, for positive number n, and this number actually for positive integer n. Okay, so we are actually here starting at 0 and going to n. And look, this is, so we write it as n factorial, and this is equal to 1 times 2 times 3 times 4 times until n minus 1, n minus 1 times n. So look, factorial. So the exclamation mark after the number is telling you that you need to multiply every consecutive number right until this number. However, there is one additional information I need to tell you here, is that 0 factorial is equal to 1. take those and write them using factorials. And look, what do we have here? Here we have 1 times a0. I can write it as 0 factorial times a0. Over here, what can I write? 1 factorial times a1. Over here, 2 factorial times a2. Over here, 3 factorial times a3. Now, here we're going to have 4 factorial times a4. Of course, here 5 factorial times a5. And finally, n factorial times an. Okay, and look. Now, we have calculated all of those expressions and remembering what we had to begin with, right? Because what did we have to begin with? We started with this, right? So, at the beginning, what we know is power, in the highest power, plus we know the values of all the coefficients, right? So what we do not know? Well, we do not know what are the values, what are the values of these derivatives. But if we are able to evaluate this at different derivatives, we will be able to find them, right? And look, out of these expressions, we can calculate directly any coefficient. What do I mean by that? Look, if I'm going to solve this for a0, what am I going to get? a0, if I divide both sides by 0 factorial, is equal to f of 0 divided by 0 factorial. Over here, a1 is f prime of 0 divided by 1 factorial. And of course then we will have a2 equal to f base of 0 divided by 2 factorial. a3 will be third derivative evaluated at 0 over 3 factorial. And of course we could go on like this until we would stumble on the coefficient an, which is equal to nth derivative of function f evaluated at 0 divided by n factorial. Okay, so what have we established this far? Well, what we can see over here is that we take the original polynomial function, we differentiated it enough times, and now we are able to rewrite exactly the same function completely in the terms of its derivatives. Okay, and look, so now we can write that if this is our polynomial function, then Maclaurin series of a polynomial function is. Okay, and look, all we've got to do is to take the function we've got and substitute what we had over here. So we've got f of x is equal to a0. a0 is equal to f of 0 over 0 factorial. And look, we don't need to write it. However, just so you see please remember that over here I can put x to the power of 0, which is 1. Okay, then we've got a1 times x, so we've got f prime of 0 over 1 factorial times x. However, again, please remember that x is the same as x to the power of 1. What will we have next? F is 0 over 2 factorial x squared. Then, third derivative of evaluated at 0 over 3 factorial x cubed. And where do we finish? Look, of course, the last component is component n. So instead of an, we write nth derivative evaluated at 0 divided by n factorial times x to the power of n. And look, this series allows us to give a perfect representation of this polynomial function in terms of these expressions that you see over here. And those expressions, of course, are associated with derivatives. Because our polynomial has n plus 1 different components, right? Because we also need to calculate 0. This will also have n plus 1 different components. And the thing is, we've actually shown that regardless of what is over here instead of a0, a1, and so forth, we can always find those values using these expressions. Okay, I realize that at this moment it might not seem like a lot to you. However, let me just tell you that it has incredible applications. However, we will see them a little bit later once we start complicating things here a little. Okay, before we move to another part, let's just do a very simple example that should illustrate to us how this rule works and if it actually works, right? So, let's just say that we've got a polynomial function 2 plus 4x plus 2x, 3x. Okay, so first thing, I evaluate this function at 0, it is equal to just 2. The next thing I do is I calculate the first derivative, right? I evaluate it at 0. This is 4. Then I calculate the second derivative, and I evaluate it at 0, which gives me 6. Okay, now let's use the formula. What do we should have here? Here we have 3 components, so our formula, of course, should also have 3 components. So we will have here f of 0 over 0 plus f prime of 0 over 1 factorial times x plus f piece of 0 over 2 factorial x squared. Okay, so what do we have here? 2 divided by 1 is 2. Then we've got 4 divided by 1 is still 4. And finally, here we will have 7 It works very, very well. So, what we can get from this is that now we know that there is a way how we can change a given polynomial function into a different alternative representation that will give us eventually exactly the same result. Okay, this is it. In the next video, we're going to start with the Taylor series. That is another step and builds up on the Maclaurin series. Thank you for your attention.